All right, welcome to the deep dive. Today we're diving into a particularly interesting piece of research.
Yeah,
And what makes this one kind of unique is that we actually have one of the authors of the paper joining us for this deep dive.
that's right.
And you, our listener, have told us that you are interested in a little bit more of an academic explanation, especially because of the innovative nature of the paper.
Yeah, exactly.
So let's talk about it.
All
This is
right.
some really cutting edge work in language model adaptation, right?
Yeah, so the paper we'll be discussing today is called State Tuning, State-Based Test Time Scaling on RWKV-7.
Okay,
It's authored by Xiao, Zhiyuan, and myself, Yueyu.
great.
And yeah, today we're going to be talking about all the different state tuning techniques that we developed for RWKV-7, or as many people know it, the Goose model.
The goose model, okay. And, a problem that we see constantly in the world of large language models is how do we get the power and intelligence of the biggest models into smaller, more efficient ones?
That's exactly right.
It's this trade-off between the two, right?
Yeah, so large language models like, ChatGPT, Bard, all these big models, they can do amazing things. You can, have them write you poems and stories and even code. But the issue is they're extremely resource intensive. Training them requires huge amounts of data and compute.
Massive.
Um, and so smaller models are, they're more practical in a lot of ways, but they often can't do all the things that the bigger models can.
Right.
And so our work tries to kind of find a good middle ground between these two extremes. We want to find a way to enhance the abilities of a smaller model without having to pay the full cost of training a huge model.
Okay.
And, state tuning is our proposal to kind of solve that problem.
Okay, and you guys actually propose 4 different methods in the paper to tackle this, right?
That's right. So at a high level, we start off with this idea of standard state tuning, which lays the groundwork for everything else.
Right.
Then we move into this idea of dynamic scaling with a kernel method, where we try to expand the representational power of the model.
Got it.
Following that, we've got DBP-enhanced dynamic state tuning. And this is where we actually use decorrelated backpropagation to help with the training process in this higher dimensional state space.
Yeah.
And then finally, we talk about test time scaling with larger model guidance. And this is very unique because it allows you to adapt the model's state at inference time.
Wow. So even as it's making predictions, it can adapt.
Exactly.
That's fascinating. So we're going to really go in depth into each one of these. We want to understand, not only the how, but the why behind these innovations, why they're novel, and what kind of potential they unlock, right?
Absolutely.
So let's just start from the beginning. Let's talk about standard state tuning.
Okay.
When we talk about the RWKV-7 model and this idea of a state matrix, what exactly are we talking about?
Right. So RWKV-7, it's a recurrent-like model, but instead of having a hidden state like a traditional RNN, it uses a state matrix. So we denote this as and dollars, and I think of this as like the model's dynamic memory bank. As the model is processing a sequence of words, this matrix is constantly being updated.
Okay.
And it has dimensions n dollars, where n dollars is derived from the model's overall size. So C dollars is the size, and high dollars is the number of attention heads. You just divide those two, and that's how you get dollars. And basically, the bigger this dollar is, the more information the model is able to store and process at each step.
Okay.
And so, the state matrix is super important because it allows the model to kind of integrate all the information it's seen so far and use that to help it understand the current input.
Got it. So it's like it has this short-term memory that it's actively updating as it's going through the sequence, right?
Exactly.
So then what is standard state tuning?
Right. So standard state tuning is this idea that instead of, fine tuning to entire model when we want to adapt it to a new task, we could just focus on this state matrix, dollars.
Okay.
So we keep all the other pre-trained parameters of the model frozen, and we just adapt the state matrix.
That's really interesting.
And, what's cool about this is that you can actually achieve a lot of adaptation just by changing this state matrix. You don't need to modify the fundamental knowledge that's already been learned by the model.
Okay, so how do you actually do that?
Right. So in practice, what we do is we initialize a new state matrix.
Okay.
And this is usually done with zeros or, just small random values. And then during the training process on this new task, we only update the elements of the state matrix.
Okay.
And we do that based on, the errors that the model makes.
Got it.
All the other weights, the pre-trained weights that transform, the words into their vector representations, those are kept frozen.
Okay, so what are the main advantages of this?
Yeah, so the biggest benefit of this is that it's much more efficient than fine-tuning the entire model,
Okay,
right? Because you're not updating, billions of parameters. You're just updating this one matrix, which is much smaller.
right.
And so that means that the training process is faster, you need less data, and it's just overall more computationally efficient.
Makes sense. So you guys saw some pretty impressive results with this standard method, right?
Yeah, so we tested this on a bunch of different benchmarks like MMLU, GSMAK, Wino Grande, ARCC. These are all like standard language model benchmarks that test things like, general knowledge, math reasoning, common sense reasoning.
Really broad.
Yeah, all sorts of stuff. And we consistently found that standard state tuning was able to improve performance by about 10% relative to the baseline.
That's a really good starting point.
Yeah.
10% is a huge gain, especially for, as you said, not having to update the entire model. That's really impressive. So let's move on to the second technique, dynamic scaling with a kernel method. So the idea here is that we want to enhance the expressive power of the model.
Yeah.
What are the inherent limitations of having that fixed size state matrix?
Right. So the fixed size state matrix works well in a lot of cases, but it can become a problem when you're dealing with tasks that are super complex.
Okay,
Right? Maybe they have really long range dependencies or they require the model to understand very subtle patterns.
got it.
And so the issue is that the model can only store so much information in the state matrix, right? It's limited by those dimensions, sometimes dollars.
Yes.
And so at some point you just run out of space.
Right.
And so dynamic scaling tries to solve this by essentially increasing the size of this internal memory.
Okay.
Um, but we don't want to add new tradable parameters to the core model because then we lose the efficiency gains that we get from state tuning.
Right.
So we want to find a way to scale the state without added new weights.
And that's where the kernel method comes in, right?
Exactly. So in dynamic scaling, what we do is we take that original state matrix at times m dollar and we upscale it to a higher dimension, m times m dollar dinadrol,
Okay.
where m dollars is significantly larger than dollar. And then we use a kernel method to map the model's internal representations into this higher dimensional space.
Got it.
So basically, instead of working with those dollar dimensional vectors directly, we're going to transform them into bad dimensional vectors using this kernel function.
Interesting. So you're not changing the original architecture or adding weights. You're just finding a way to, as you said, scale those internal representations up.
Exactly.
And so what kind of kernel are you using here?
So we primarily use a Gaussian kernel, and that's defined as UBV GABIDU.
Gaussian.
And so what this kernel does is it basically measures the similarity between two vectors, U dollars and $4,
Okay.
based on their distance in this high dimensional space.
Got it.
And so we have this parameter, gamadar, which kind of controls the scale of the kernel.
Okay.
And in our experiments, we either set that based on the original state dimension, or we just use a fixed value like 0.1.
Got it. Got it.
So essentially, this kernel allows us to compare vectors in a more nuanced way
Okay.
than just looking at their Euclidean distance.
Right. Right.
Because it takes into account, how similar they are in terms of their features.
So how do we actually go from that original dimensional space up to the dimensional space?
Right. So to do this, we need to choose a set of what we call support vectors.
Okay.
And these support vectors are basically points in the original dollar dimensional space. You can pick them randomly, or you can choose them more strategically.
Okay.
And so we'll have dollars of these support vectors, and they'll be denoted by,
Got it.
and then for each of our internal representations, so, BODAT P, TT, 8, VT, gets periodic, those vectors we talked about before,
Yeah.
we basically calculate its similarity to each of these support vectors using the Gaussian kernel.
Okay.
So we end up with Unstahler similarity scores, which gives us a new bound dimensional vector. So for Redo, it'll be like high Vero, and same for the other ones.
So now they all live in that higher dimensional space.
Exactly.
So how are these new psi dollar vectors used to update the state matrix?
Right. So now we have this upscaled m times m dollar state matrix, which we initialize, and then we're going to be optimizing this matrix during training.
Okay.
And we basically update it using the same update rule that we use in the original RWKV-7 model, except now we're using these mirror dimensional vectors instead of the original dollar dimensional ones.
Got it.
So it's the same operations, but we're doing them in a richer feature space.
Okay, and then how do you get back to the original dimensions for the output?
Right. So once we've updated the m times m state matrix, we compute the output in this high dimensional space, and then we use a fixed projection matrix to project it back down to the original dollar dimensional space.
Okay.
This projection matrix, we just initialize it randomly, and then we keep it frozen during training. It basically just learns to map the relevant information from the high-dimensional space back down to a manageable size.
Okay, got it.
So the key here is that we're only optimizing this upscaled M times M times M state matrix.
Right.
We're not touching the original pre-trained weights, and we're not touching this projection matrix.
Right. So the adaptation is coming solely from the dynamics within that higher dimensional space, right?
Exactly.
So it's more complex, but it's giving us more power, right?
Yeah, so the main benefit here is that we have this increased capacity to model more complex data distributions. Okay. And by introducing this nonlinearity through the kernel function, we're able to learn more intricate patterns and relationships that a fixed-size linear state might miss.
Yeah.
And we actually found that dynamic scaling consistently outperformed standard state tuning across all the benchmarks that we tested.
Okay, so that extra computational effort is paying off in terms of performance.
Exactly.
Okay, so then let's talk about the third technique, DBP-enhanced dynamic state tuning. This builds on dynamic scaling,
Yeah.
but it incorporates decorrelated backpropagation. What are the unique challenges of training in these higher dimensional spaces that we've created?
Right. So training in these higher dimensional spaces can be tricky
Okay,
because when you have a lot of dimensions, you can run into problems with optimization efficiency.
okay,
And also, the representations that you learn can be harder to interpret.
got it.
And so one of the main problems is that when the features in this high-dimensional space are highly correlated, it can make the training process slower, and it can be harder to kind of disentangle what's really going on.
Okay.
Like, what are the underlying factors that are driving the model's behavior?
Right, right.
And so that's where decorrelated backpropagation, or DBP, comes in.
Okay, so what is DBP in its original context, and how did you guys adapt it for this state tuning framework?
Right. So DBP was originally developed as a technique to improve the training of deep neural networks.
Okay.
And it does that by reducing the redundancy in the signals that are passed between layers. Okay. So the basic idea is that you want each layer to learn features that are more independent and informative.
Got it.
And that can lead to faster and more stable training. And so in our work, we took this idea of DBP and we applied it to the kernel transformed inputs to the state update.
Okay.
So instead of just using the raw kernel features, we want to try to decollate them before we use them to update the state matrix.
So you're adding a step in there where you're essentially cleaning up the information.
Yeah, exactly.
Before you feed it into the state matrix.
Right. We want to get rid of the redundant information and just focus on the most important features.
Okay, so how does DBP actually achieve that decorrelation?
Right. So what we do is we introduce a decorrelation matrix,
Better?
dollar. And this is a matrix with dimensions min times m dollar, where min is that upscaled state dimension that we talked about before.
Got it.
And this matrix is applied to each of those kernel feature vectors, the phi, kaths, and so on,
Yeah.
to produce a decorrelated version of the vector.
Okay.
So, for example, instead of using W dollar directly, we'll use W dollar, which is just Rhi dollar times.
So you're doing a transformation on those features before you feed them in?
Right. And then we modify the state update rule to use these decorrelated vectors as inputs.
Okay, so now this rival matrix, this decorrelation matrix, how does it actually get learned and updated?
Right. So Rho dollars is a learnable parameter.
Okay.
We don't just keep it fixed. And to encourage this decorrelation of the feature vectors, we introduce a decorrelation loss, math keys dollars. Okay. And this loss basically measures how much statistical dependence there is within those decorrelated feature vectors.
Got it.
And it penalizes high correlations.
Okay.
So basically, we're trying to make sure that the features are as independent as possible.
Makes sense.
And this loss has a parameter kappa dollars,
Okay.
which we set to 0.5 in our experiments. And that basically just controls the balance between different aspects of the decorrelation.
So how does that decorrelation loss affect how dollar is learned?
Right. So we jointly optimize both the upscaled state matrix and the decorrelation matrix by dollar.
Okay.
And to do this, we use different optimizers. So for the state matrix, we typically use Atom,
Okay.
which is a good optimizer for adapting the learning rates for each parameter.
Yeah.
And then for the decorrelation matrix for dollar, we found that stochastic gradient descent, or SGD, worked really well.
Okay.
And so the overall training objective is to minimize a weighted combination of the task-specific loss
Right.
and this loss.
Got it.
And so by optimizing dollars in this way, we're basically conditioning the information that flows into the state update
Yeah.
and making it more conducive to learning distinct and valuable features.
Interesting. So you're not just expanding the space,
Right.
but you're really actively managing the information flow within that space
Exactly.
to get better learning and better representations, right?
Right. And this leads to some pretty substantial improvements in performance.
Okay.
So, for example, on MMLU, we get 79% accuracy with DBP compared to like 71% without it. On GSM-8K, it's 89% versus 80%. And similar improvements on Wino Grande and ARCC.
Those are huge jumps.
Yeah, so DBP really helps to improve both the convergence speed of training
Okay.
and the quality of the representations that we learn.
Very, very cool. Okay, so we've talked about optimizing the state during training. Your fourth technique, test time scaling with larger model guidance, is really fascinating because it's adapting the model's state even as it's making predictions.
Exactly.
So walk us through this. What does this look like in practice?
Right, so the idea here is that instead of having a fixed state matrix that we use for all inference, we can actually adapt the state matrix at inference time.
Okay.
And we can do that by using a larger language model to guide the state tuning of our smaller RWKV-7 model.
Got it.
So basically, the larger model acts as a teacher, and it helps the smaller model to reason more effectively.
Interesting. And you're doing this with reinforcement learning, right?
Yeah, so we use a combination of reinforcement learning and chain of thought prompting.
Okay, can you explain how that works?
Right, so let's say we have a complex question that we want to answer.
Okay.
First, we're going to prompt the larger language model to generate a chain of thought,
Okay.
which is basically a series of intermediate reasoning steps that lead to the final answer.
Got it.
And then, as our RWKV-7 model is generating its own response to the question, we're going to slightly adjust its state matrix at each step to encourage it to align with the reasoning steps that were provided by the larger language model.
Okay.
So it's like we're giving the smaller model a step-by-step guide on how to solve the problem.
Got it. So you're using that pane of thought from the larger model to kind of nudge the state of the smaller model in the right direction.
Yeah, and to quantify how well the smaller model is aligning with the larger model's reasoning, we define a reward.
Okay.
And this reward is based on the log probability of the RWKV-7's output at each step, matching the corresponding step in the larger model's chain of thought.
Okay.
So if the smaller model generates a word or a token that has a high probability, according to the larger model's reasoning, then it gets a higher reward.
Makes sense.
And then we use gradient descent to optimize the state matrix of the RWKV-7 models during inference
Okay.
to try to maximize this reward.
Got it.
So basically, we're taking small steps in the direction that makes the RWKV-7's output more likely to align with the larger model's reasoning.
So this is all happening as the model is generative its answer.
Exactly.
Wow, that's pretty incredible. And what are the advantages of adapting the model in this way?
Yeah, so the main advantage is that we can now handle much more complex tasks that require multi-step reasoning,
Okay.
right? Because we're essentially mimicking the thought process of a larger and more capable model.
Right.
And so the smaller RWKV-7 model is able to achieve a higher level of accuracy on these challenging tasks.
So it's almost like you're getting the benefit of the larger model
Yeah, in a way.
without actually having to run the larger model.
Right, because the larger model is only used to generate the chain of thought.
Got it.
And then the smaller model is actually doing the inference.
And you said earlier this performs really well, comparable to DBP.
Yeah, so we found that test time scaling with larger model guidance actually performed really well, and it was often very close in performance to DBP enhanced tuning,
Wow.
which is really exciting because it suggests that we can get, really significant improvements in performance without having to do any task-specific training data or offline tuning.
Right.
We can just adapt the model on the fly at inference time.
That's amazing. But it does seem like it requires that we have access to this large language model during inference, right?
That's right, yeah. That's the one drawback of this approach.
So that might not be practical in every single situation.
Exactly.
Okay, so we've talked about standard state tuning, dynamic scaling, DBP-enhanced dynamic scaling, and now test time scaling. What are the overarching implications of this research?
Right, so I think the key takeaway here is that state tuning, in all of its various forms,
Yeah.
is a really effective and efficient way to improve the capabilities of smaller language models
Okay.
without having to do full fine-tuning. Okay? Right. And this is really important because it means that we can deploy more powerful language models in settings where resources are limited,
Right.
and it also means that we can adapt models to new tasks much more quickly.
Yeah.
So I think state tuning has a lot of potential to make language models more accessible and more useful in a wide range of applications.
And it's really interesting how each one of these techniques builds upon the previous one, right?
Exactly.
Like standard state tuning lays the foundation,
Yeah,
and then dynamic scaling comes in and gives us more power.
right.
And then DBP further improves that training process.
Yeah,
And then test time scaling is just this whole other level of adapting the model.
exactly. So it's really cool to see how all these techniques kind of fit together.
Yeah, it's amazing. So where do you see the future of this research going? What are some of the most promising directions?
Yeah, so there's a lot of exciting directions that we can go from here. So for DBP, one of the main things that we want to look at is how to reduce the computational overhead.
Okay.
Because right now, DBP can be a little bit expensive to run.
Right.
So if we can find ways to make it more efficient, then it'll be more practical to use in a wider range of settings.
Yeah, makes sense.
Um, and then for state scaling, we could explore different kernel functions. Okay. Or different ways of selecting those support vectors
Yeah.
to see if you can get even better performance.
Okay.
And then for test time scaling, one of the big challenges is how to reduce or eliminate the reliance on the larger model during inference.
Yeah.
Right, because as we talked about, that can be a limitation in some cases.
Right.
And so maybe we could look into techniques like distillation
Okay.
or pre-computing some kind of guidance strategy that we can use at inference time.
Got it.
And then more broadly, it would be really interesting to see how these state tuning techniques work on a wider range of tasks and different neural network architectures.
Yeah, see how far we can take this.
Exactly. And of course, we need to analyze the memory and latency implications of each of these methods
Right.
to make sure that they're actually practical to deploy in real-world settings.
For sure. For sure. It's so cool to see these different approaches tackling that fundamental problem of efficiency versus capability
Yeah.
in such distinct ways, right?
Yeah.
You've got DBP and test time scaling, which are a bit more expensive, but they deliver that high performance,
Right.
which is really promising for creating more powerful and adaptable language models.
Yeah. I think the results that we saw with DBP and test time scaling are really encouraging because they show that we can actually get really close to the performance of these huge language models
Right.
while using a model that's much smaller and more efficient.
So it's not just marginal gains.
Right.
It's like a fundamental shift in how we're thinking about models.
Exactly.
That's amazing. Well, thank you so much for taking us on this deep dive into the world of state tuning for RWKV-7. Our listener now has a much better understanding of all of these techniques and how they work and the innovations behind them.
Yeah. And I hope this discussion has kind of sparked some new ideas and got people thinking about the future of language model.
For sure. And we'll leave our listening with this thought. We've seen how successful it can be to optimize the internal state representations of a model. So what other things within neural networks could we target and optimize for better adaptation and performance without needing to retrain the entire model?
That's a great question.
It's a big question
Yeah.
to think about going forwards. Well, thank you again for being here and sharing your expertise on this really fascinating research.
Thanks for having me.
This is a great discussion.
It was fun.
I'm glad you enjoyed it.
I did.
All right. And to you, our listener, thanks for joining us for another deep dive. See you next time.